Hello, and in this video, in the second part of this chapter, we're going to be looking at kinetic and potential energy. So potential energy is basically like gravity. So kinetic and gravity, essentially. And so last time, as a recap, we looked at work. So I've got this example here. So we looked at work done, which is basically the sort of the energy we use to push or move an object forwards, right? And so we saw that work done is force. So how much physical force onto the object to move it, and then the distance. So how far are we moving the object along, right? So that's the idea. Work done basically telling me how much energy I'm putting onto the object, how much energy I'm transferring onto the object, and then moving it about, right? Essentially, that's all it is. So work done is telling me how much, and work done is in joules, so it is a type of energy, and it's specifically again the energy I'm transferring and putting onto the object to move it. And that's all it is. Energy I'm putting onto the object to move it. Okay, and so so in this example as well, then this person is transferring their energy onto the box. So the box is gaining energy. Now, what is this energy transferred into? Well, kinetic and potential energy. So kinetic energy, you can imagine you're going to need kinetic energy to move forward, right? And so that's the first example we're going to be looking at. So if I draw just a very simple diagram. So let's say a similar sort of example. Let's say I have a box again. Have a box, and it has a and it's moving forwards, and then after some time it ends up here. So we've got two different positions. Position 1, position 2. So at position 1 it has speed. I'm going to say u. Okay, u meters per second. My initial speed. And then after it moves forward, then it has a different speed v. Okay, if you have looked at Survey, you'll be quite familiar with this sort of setup. But that's the idea. I'm in two different the box is in two different positions as it moves forward. So it starts with speed u, then ends up with speed v. Okay, so the kinetic energy then. So in general, kinetic energy is calculated by this formula here. So kinetic energy, which you might be familiar with from GCSE physics, it's a half mv squared, where m is the mass and v is the velocity or the speed. Okay, and there we are. Okay, so that is my formula I will be using here. There. Okay. And so in this example then, so if I was to calculate the kinetic energy at these two parts of the journey, so it starts at position 1, so I'm going to say my initial kinetic energy, Ke. Okay, so if we look at this position here, where the box starts at, the initial speed is u. Okay, and I'm not specifying the mass, I'm just going to call it m, so it's going to be half of the mass times the speed, which again I've called u, so that's my start speed, and so it'd be u squared. Okay, then my final kinetic energy, so when it reaches the second point here now, it has speed v. Okay, so it's very simple, it's then going to be half mv squared. And so there we are. So you can see the kinetic energy will change as your speed changes. Okay. And so then, if I was to calculate then the change in kinetic energy throughout these 2 points, so the change in Ke, the kinetic energy, it's going to be, well, okay, the change, so we end up with well, we're going to be taking them away, right? So it's going to be half mv squared take away half mu squared. Okay. And so there we are, right? The change of kinetic energy. So we take away from the two different energies that we have. Okay, so why do I bring this up? Well, this links the work. Okay. Now, as I just briefly outlined, when I talked about this example, the work done. So the work done, so the work that the person is doing to push the box forwards, right? The work done, so the person is transferring their own energy, putting their energy onto the box to move it forward. So the box gains energy. And so specifically, because the box is moving forward, it gains kinetic energy as the person pushes the box forward. Okay, so it gains kinetic energy. Now, what that means is then, with the example I've just done here, is actually this change in kinetic energy, right, that the box is gaining, is as a result of the work done to move it forward. So actually, it turns out we've got a sort of another formula that the work done to move an object is equal to its change in kinetic energy in this sort of scenario. Okay, and so this is what we'll be using. Okay, these two ideas here. Okay, so that's sort of the idea we're going to be looking at. So let's have a look at some examples. Okay, so firstly, here I'm told a particle of mass 0.3 kilograms is moving at a speed of 9 meters per second. Calculate kinetic energy. Well, actually, this is just using the formula quite nicely because remember, as we just said, the kinetic energy, which you do need to know, it's not in any formula book, but hopefully it's simple enough. The kinetic energy is half mv squared. Again, m the mass, v the speed we're dealing with. Well, in this case, we've got our m, our mass to be 0.3, and your v, your speed is 9. So therefore, that means the kinetic energy of the particle, so the object essentially, that's going to be half of 0.3 for m, and then 9 squared for v. So simply put that in the calculator. We get 12.15, and that being joules because it's an energy, right? And so there we are. Here we're told a box of mass 1.5 kilograms is pulled across a smooth horizontal surface by horizontal force. The initial speed is u, and the final speed is 3. Work at, the work done by the force moving it forward is 1.8 joules. Calculate the value of u. Okay, so again, if we then sort of draw a situation, so it's we're on a smooth horizontal, which means it's like this again, right? It's like a sort of table. So we have a box, we draw our box again, it's just a little rectangle. The mass is 1.5, add that on. Then we're told it's pulled across by a horizontal force, so it's going to be moving forward by some force. I'll call that D. Okay. Right. I'm told the initial speed is u, so let's say over here the speed is u, and then at the end the final speed is 3. So those are my two speeds, right? U and 3. I'm also told the work done by the force is 1.8 joules. Okay, so this force D that's pulling it forward, the work done is 1.8. Okay. Now, you might be thinking, well, work done is force times distance, right? Um, I think that could be quite complicated because we're not given the distance, and actually we don't know what the force is either. So we're missing both of these ingredients. But as we discussed at the start in this second formula, actually the work done when we're moving something forward or moving something in general is just the change in its kinetic energy. Okay, because remember the energy we're transferring to move an object forward has to be converted to kinetic energy, essentially. So the result of the change in kinetic energy is the work done. So we can use this instead, and we can work out the kinetic energies this way. So there we are. Okay, so we know that the change in kinetic energy then is the work done, and we're told it's 1.8 joules, so 1.8. There we are. Cool. Right, so then we just need to work out the change in kinetic energy. So we need the kinetic energy at these two different speeds. So the initial speed is u, again. Initial speed is u, so the initial kinetic energy at that speed is going to be half of m, the mass is 1.5, times u squared. So half times 1.5 is 0.75 u squared. Okay, then the final kinetic energy is at the final speed, then that's going to be half of 1.5 of the mass times 3 squared, because again the speed is 3 at the end. So if we work that out, that is 6.75. Cool. Okay, so then that means the change in kinetic energy, well, it's going to be the final take away the initial kinetic energy, so 6.75 take away 0.75 u squared. Again, that comes from here that we just worked out. That's going to equal to the given change of 1.8. And so at that point, again, similar to the last example, we just solve for u here. Okay, so what we can do is say 0.75 u squared by doing 6.75 take away 1.8 is 4.95. So we're just solving this equation now. And so then divide by 0.75, so u squared is 6.6. And so therefore, if we square root that, u is going to be root 6.6, which is 2.57 meters per second. It's a speed at two decimal places. And so there we are. That is u. Okay.